Okay, so let's talk about something that it's important to understand at least a little bit. So even if we don't develop a great mastery of this topic in the next hour and a half, you should at least have some understanding of what this word means and how it gets used in the SEM community, because they use it in a very specific way. This term identification or model identification, or whether or not a parameter is identified, or parameter identification. There are important limits on what we're able to do with our data when we start estimating statistical models, path models, and structural equation models, and some of those limits and constraints that we have are going to be fall under this topic of identification. One general way of understanding this term: parameters or models are identified if they can be estimated. That might be one way to say it. Now, if you're in economics or econometrics, you understand identification, model identification, or parameter identification, well, perhaps in a couple of different ways. Maybe in econometrics, one of your definitions would be a parameter is identified in a given model with a given estimator if the result we get is the change in the dV we would get by intervening along the IV, the independent variable, in some specific way. You might give identification kind of a causal interpretation. In the SEM community, we have a different kind of definition. It's not specifically related to assumptions of causality necessarily. It just has to do with whether or not Mplus is actually able to give us a result. If it's actually able to converge when it's using the ML estimator and give us a parameter estimate. For us, it's going to relate to the extent to which we have enough information in our data set to give us a unique maximum likelihood estimate for our parameters. And you'll see kind of how it works and the rationale here in just 1 second. For example, if I don't have any data, if I've measured nothing, can I interrogate those data to look for a correlation between satisfaction and performance? I can't, because I don't have any. I need at least, right? I need satisfaction and performance in my data set, and I need their observed correlation. And then I can use that as my estimate. But if I don't have that information in my data set, if it's not there, then when somebody says, hey, why don't you tell me what your best guess is for the correlation between job satisfaction and job performance? Then I'll say, oh, I don't know, 0.2, 0.3, 0.5? I don't know. I could give you any one of those, and they would all be equally likely, because I don't know. I don't have any data. So I need some information that I can rely on to give you my best guess. Don't get me wrong, I can give you a bunch of guesses. I can give, right, they can range anywhere from -1 to +1 if it's a correlation. But I can't definitively give you my best guess. Because if I don't know anything, or if I don't have enough, right, if I don't know anything, then all guesses are equally likely. So that presents problems for methods like maximum likelihood that are trying to give you the most likely parameter estimate, that are trying to give you not just a guess, but the best guess. So if at least two numbers are equally likely, there is no best guess. It'll say, well, how about this one? How about this one? How about this? We don't know. And then it doesn't converge on a single estimate, because there is no best guess. So we need to give Mplus enough information to give us not just any guess, a best guess. The best estimate, the most likely estimate of a parameter. So I've revised, this is just like fit, model fit. This is one that we quite often kind of lose some people on, at least in terms of interest for sure. But also combined with that is kind of some of the substance there. So I've tried to revise it, and we'll see if it works better. if you're here for the second time, then you can let me know what you think. So there are some rules of thumb that you can use. Sorry, I'm just trying to get off my feet, but it's not really working. So there are some rules of thumb that you can use to know whether or not you do have enough information in your data set to get a best guess, to get a most likely estimate, or an estimate that is unique in that it's maximizing the probability of the data given the model. That's another way to say it. So you can look at Kenneth Boland's T rule, and basically it's a way of kind of counting up the amount of information that data gives you and the amount of information required to estimate the unknown parameters. So if we want to estimate a correlation between job satisfaction and job performance, we want to estimate that correlation, we've got to measure both of those variables, right? And then we can use the observed correlation to make our guess, right? As the estimate. We can say, well, we don't know what this is in the population, but when we look at our sample, because we measured both of them, we're going to assume they're normally distributed. They both have a mean, they both have a variance, and they both have a covariance. And because they have they don't both have a covariance, they have a covariance. And because because there is some covariance there, that's the information we're going to use to give you the estimate of how they're related to each other. So we can't talk about covariance if we don't have one in the sample. So the information we get from the data are those things, means, variances, and covariances. And we're going to rely on those to estimate our unknown parameters. So this T rule is like saying, hey, it's like degrees of freedom. Do you have non-negative degrees of freedom? Is there more information in the data set than you're trying to estimate in your model? Or are there more parameters implied by your data set than you're trying to estimate in your model? So we're going to run through it and kind of play a little game. Is it identified? Is it not? And someone's going to go home with a new car. No, this isn't Ellen. Or what's the other one? Oprah. Yeah, she's got better gifts probably. She's got more money. Someone gets a new plane. Like how she's considering running for president. Like, oh, you had a talk show for 30 years. How are you qualified to be president? Our standards are quite low. I mean, look who's in there now. Jesus. I mean, I'd take Oprah over that any day of the week. Don't get me wrong. Just because she's a lot better doesn't mean she's the best we can do.
She's a self-made millionaire.
Yeah, exactly. Yeah, exactly. Yeah, exactly. Right. So, with our maximum likelihood approach, we're only estimating parameters based on the data. If we use a Bayes estimator, that's not true. We also have these priors. So parameter identification is a little trickier in the Bayes case. We're not really going to cover it very much because for the most part we're using maximum likelihood estimators, and that is a very technical topic with the Bayes in the Bayes case. But for the most part, whatever rules we come up with for understanding whether or not a model is identified, they're going to apply for the maximum likelihood estimator and the Bayes estimator, because by default Mplus uses these uninformative priors, so it's like we only have the data for our estimation. So basically the rules are the same for identification. We can't estimate more unknowns than we have known pieces of information. That presents a problem. So let's say that we've got a covariance matrix, sigma. And all that means is that we've measured two variables, and each one has a variance, sigma squared, and there's one covariance right there in the bottom left of that matrix. So whenever you see that big sigma, just think, oh, variances and covariances. Or just think, oh, correlation matrix and standard deviations or whatever it is. So assume we've got two variables, y1 and y2. Right? For each there's a variance, and for both of them there's a covariance. So we have 3 pieces of information here that we can use to estimate some of our model parameters. Remember, we're not saying that Mplus can't give us guesses for all kinds of parameters, but it has to be able to arrive at its best guess. It has to be able to arrive at an estimate that is more likely than all the other estimates. Otherwise, it'll just give you a handful of estimates. Oh, it could be 0.2, could be 0.3, could be 0.1. I don't know. You're not going to be able to give that to the reviewers. Well, what are the model estimates? It says it could be anything. That's not what we're here to do. Okay, so here's a term. When a parameter is, or a model, is just identified, it means that there's just enough observed information to estimate the unknown parameters that we're trying to estimate. So here's an example of that. Let's say we've got these 3 pieces of information, observed variances and a covariance. Now here we're kind of formally diagramming the variances and the covariance. So instead of just an arrow coming off, we're saying these are separate parameters that we're estimating. We're being very formal here because we want to link what gets estimated back to the information that we've observed in our sample. So if you want to estimate the variance and covariance in a model that looks like this, y1 with y2, what's Mplus going to do? Is it going to be able to estimate that model? What's going to be its best guess for the variance of y1 in the population? It's got the sample data in hand. It's just going to look at that, right? It's going to go, oh, my best guess for the population variance, the parameter estimate, is the sample variance. That's my best guess. So it can give us an estimate because it's got that in the sample. And the variance of y2 is the same. It can give us an estimate because we've actually measured those variables. We have data for them. And then we say, hey, Mplus, I don't just want the variances. I used a with statement. So give me an estimate of the covariance. Mplus says, hey, no problem. You've measured both of the variables. They come with the covariance, and this is what it is. It's going to give us the most likely estimate. And how it's going to do that is like this. It's like maybe the observed covariance is 0.5. Mplus says, hey, is it in the process of iterative estimation, it says, hey, is it 0.4? Is it 0.4? And it looks at the data and it says, no, it's 0.5. We can do better. And then it says, is it 0.45? And it looks at the data and it says, we're getting closer, but we can do better. 0.46, 0.47, 0.48, blah, 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 and it gets really close, 0.5. And then it says, what if I go to 0.51? Well, in the data, it's 0.5. So if we move away from that estimate in the opposite direction, it makes the model, the parameter estimate less likely. So it says, 0.5 is my best guess. I'm done, because I have a best guess. If I move away from this estimate, either up or down, the fit gets worse. So I can stop estimating, and there's your result. You say, oh, okay, thanks. You could have just looked at the sample statistics, but that's not really going to help us here when we're talking about identification. This model is just identified, because you have just enough information in your sample to get the best guess that Mplus can give you. The maximum likelihood estimates. Does that kind of make sense? How it's using the observed data to do this estimation. So the data need to have the required information. Okay, this model is just identified. How many degrees of freedom does this model have? We've got 2 variances and a covariance in the sample, and we're estimating exactly those things, 0 degrees of freedom. It's just identified. This will converge, we will get estimates with df equals 0. It's just identified. So we can estimate this model, just identified.inp, and let's see what we get in Mplus. And this is what's new. We're actually going to estimate something. And look at what we get. Day 3, session 4, just identified 1. So it's all of this same Matthew and Far data that we just worked with, except I renamed OC1 and OC2, Y1 and Y2. Doesn't matter, they're just those OC variables. And then down here, use variables are Y1 and Y2, which is actually just OC1 and OC2. And now Y1 with Y2. Let's see what it tells us. We scroll down. We don't have any major errors. And what's the chi-square test to model fit? There's nothing. No degrees of freedom and no chi-square. It fits the data perfectly because there are two observed variances, one observed covariance, and we're estimating exactly those things. So there's no deviation in our estimates from the observed data. The fit statistics don't even make any sense. Of course it fits the data perfectly. Of course there's no error or residual left over down here. The model is just identified, and the estimates it's giving us fit the observed sample perfectly. So it's just identified. What about this? What about this next case? What happens if we say Y2 on Y1? How many parameters are we estimating? 3. Y1 has a variance. Y2 has a residual variance. And then there's a slope relating Y2 and Y1. So, where's the information going to come from to estimate those? The two variances and the covariance. What will the residual be when it estimates it for Y2? It will be whatever's left over after you account for the covariance, and which is what the slope is doing. So there's just enough information here to estimate this model. It's still just identified. The beta is going to be estimated based on the covariance and the variance of the predictor, and the residual is a function of the covariance and the observed variance for Y2. Again, it's just identified. So if we estimate this, again we'll get 0 chi-square, 0 degrees of freedom, there is no p-value, the fit is perfect. Is that okay? Does that make sense? And then you've got it there, obviously. You know what it'll say. It'll be an on statement. You've got that input. What about this case? Y1 variance, Y2 variance. Is there a slope or a covariance there? No. This model, we would say, is over-identified because we've got information about their covariance in the sample, but we aren't telling Mplus to estimate any parameter that would use that information. It's like the sample has more to give us than we're using. It's over-identified. We have positive degrees of freedom. How many parameters are we estimating? 2. How many parameters exist in the data? 3, exactly. So we'll have 1 degree of freedom because we've got more in the data set than we're estimating. Now, are we going to have a non-zero chi-square? Well, what if the observed covariance was 0? Then we wouldn't need to estimate 1, right? But if the observed covariance is non-zero, which it's definitely not for items OC1 and OC2, they're really strongly correlated, then this model isn't going to be able to fit the data very well, is it? Because it's not going to be able to account for their observed covariance. It's going to give us the best estimates of the two variances, which are just going to be exactly what the observed variances are. But it's probably going to have a poor fit to the data. This model is over-identified. More information in the data set than we're estimating. Well, that's always how I say it. That's not very precise or even necessarily accurate. But it's one way to think about it. So let's go to over-identified 1.imp. scroll down, y1, y2. Remember, when we refer to a variable, we're referring to its variance in the model statement. There's no with statement, there's no on statement. So there's no regression, there's no slope, there's no covariance. So what happens when we estimate this? If we scroll down to model fit, we definitely have a chi-square value. It says reject this model in a big way. With 1 degree of freedom, is that a pretty big chi-square value? That's pretty big with 1 degree of freedom. RMSEA is huge, that's bad. These fit indices are 0. That's bad. And if we scroll down and we look at the results, oh, this is why. We have a variance for y1 being estimated and a variance for y2 being estimated, but we don't have a covariance or a slope in there anywhere. So they obviously correlate in the sample, and we haven't accounted for that with some model parameter. So our fit is not very good, but we do get estimates of the variances, don't we? It can give us its best guess for those. So the model is identified. To help you make sense of the implications here, let's pick a case where it can't give us any estimates. This is a model that is under-identified. We don't have enough information to estimate this. How many observed correlate or covariances do we have? Just one, right? One observed correlation. How many different parameters do we have that are going to rely on that observed correlation when Mplus tries to estimate them? We've got 2 different beta weights, right? We're saying, hey, y2 on y1, y1 on y2. Well, let's say that the observed correlation is 0.5 or 0. Let's say it's 0. The observed correlation is 0. Even if the observed correlation is 0, this model's still under-identified. Check it out. What should our estimates of beta 1 and beta 2 be? Well, Mplus could say beta 1 is 1 and beta 2 is negative 1. And when you sum those together, that's 0. That fits the observed correlation of 0 in that case, wouldn't it? Well, what if beta 1 was 1 billion and beta 2 was negative 1 billion? When you sum those together, it's still 0. So there's no best guess. There's no best estimate. There's no single estimate that has the likelihood maximized. You can plug in a bunch of different values, and as long as they're equal in sign and opposite in magnitude, you'll get back to an observed correlation of 0. So Mplus will try to estimate those parameters, and it'll run out of time. Essentially, it'll try 1,000 times or 10,000 times, whatever the max iterations are set to be, and it'll say, how about 1 and negative 1? Oh. How about 1,000 and then negative 1,000? Oh, that's the same thing. And it'll try and try and try and try to find the best fitting estimates, and an infinite number of possibilities exist for those parameters that fit equally well. Can't actually be 1 billion or anything else. It's constrained by the observed variances, but still. It could be, 0.00001, negative 0.00001, and then they could be adjusted by whatever. Okay, we don't have enough information to identify unique effects of one variable on another. We'd say this model is under-identified. And a nice little rule of thumb is, how many observed pieces of information do we have? 2 variances and a covariance. How many pieces of information, or rather, how many unknowns are we trying to estimate? 4. We're trying to estimate 4 unknowns, and we only have 3 knowns. So we're asking too much of the data. It's under-identified, negative degrees of freedom, and it won't converge. Let's try underidentified1.imp and see what happens. Underidentified 1. If we scroll down, what we see is y2 on y1, y1 on y2, and let's see what Mplus says. Scroll down. Warning, got all kinds of problems here. The degrees of freedom for this model are negative. The model is not identified. No chi-square test is available, and just in case that didn't make it clear, check your model. The model estimation terminated normally? Yeah, no it didn't. The standard errors of the model parameter estimates could not be computed. The model may not be identified. Again, check your model. Problem involving the following parameter. It doesn't know exactly how to tell you what that problem is. This is a specific kind of case. But look, there are no standard errors. It's got some serious problems. It can't estimate this. There's no unique solution to this problem. So we want to avoid this case. And typically, for the sake of parsimony, we want fewer estimated parameters than the parameters that are associated with our observed data set. We want an over-identified model. We want positive degrees of freedom. But mostly, surely, what we want to avoid is this, where you ask Mplus to do something that it can't do. It's impossible. You know, this is like that case where you haven't been outside for a week, and somebody asks you, what's the weather like? And you say, I don't know, hot, cold, something. Those are all equally likely. And you say, give me your best guess. You say, I don't have one. And I don't have one because I don't have enough information to even have a best guess. All guesses are equally likely. And that's this kind of case. So some people have been asking, can we estimate a CFA, can we estimate factors that only have 2 indicator variables or 1 indicator variable? This issue relates to that question. So let's work towards answering that question in a way that involves latent variables. Okay, are these models over-identified, under-identified, or just identified? Just, let's get creative. That's a stupid thing to say there. But I think the smiley face says it all. Let's just say that. Check out this latent variable model. Now we're being very formal with our double-headed arrows to indicate a variance because we want to make absolutely sure we're able to look at the parameters that are being estimated and how they might map on to the observed covariance matrix up there in the top right, or the population covariance matrix that our sample implies. So here we've got 2 observed variables and 2 latent variables. This is a weird looking model, isn't it? What is this? This is eta 1 by y1, semicolon. Eta 2, or that other latent variable, by y2, semicolon. The factor loading there is going to be fixed to 1, isn't it? Because the first indicator variable gets a factor loading fixed to 1. So the factor loadings are not estimated. That's not an unknown. That's fixed at 1. Do y1 and y2 have residual variances? They don't. They've got nothing left over. And how to specify that in Mplus would be y1 at 0. We're saying, hey, Mplus, y1's variance is 0. It's a residual variance in this case, because y1 is being predicted by eta 1. And with y2, it's a y2 at 0, no leftover variation. And then eta 1 with eta 2, that's an estimated covariance. And each latent variable has its own variance. A variance for that one and a variance for that one. If you were to write it out as a regression equation, it'd be like this. y1, boy, I haven't done this in a long time. That's kind of fun. Yeah, everybody, come on. Let's graffiti the place and then run away. The y1 is equal to what? We might have an intercept there, but it's not drawn, so let's pretend like there's no intercept. What's the slope? We could symbolize it as a lambda, but what is that lambda equal to? What's the slope? 1. Jesus. 1. 1 multiplied by what? Just so we keep it in our head what we're doing exactly. A to 1. Is there any residual? Any left over? No. So what happens when you multiply something by 1? You get that thing. So that is saying, hey, y1 equals a to 1. There's just an identity there. Is there any unknown here being estimated? Nothing. Nothing unknown being estimated. So we don't lose degrees of freedom. We're not drawing uniquely on the data to do anything, except a to 1 does have a variance, doesn't it? Well, if y1 equals a to 1, what's our best guess for a to 1's variance going to be? y1's variance. So whatever the variance estimate we get for this variable is, it'll match the observed variable's variance. And then when we say a to 1 with a to 2, well, these are just equal, right? And then y2 equals a to 2. So when we say a to 1 with a to 2, what's the estimate going to be for the covariance? The observed covariance. So is this model identified? Yes, just. It's just identified. We've got 2 observed variances, and we've got 1 observed covariance, and for some silly reason, we've told Mplus to make a to 1 equal to y1, and to make a to 2 equal to y2. And you would never normally do this. But we did it because we're practicing thinking about whether or not a model is identified. So, can you estimate a model where you have a latent variable and only 1 observed indicator? Yes. But you have to institute all kinds of constraints. You can't estimate a residual variance. You can't estimate the factor loading. You have to impose constraints on the model. Otherwise, you'd be estimating too many things. You wouldn't have enough information. You've only got 2 observed variances and 1 observed covariance.
So, like, this essentially assumes there's no measurement error in this particular case.
Right.
Right.
It'd be like saying, hey, why don't we just use the observed variable?
So, but you could also use your factor score or...
Yeah, you could. But this is a waste of the latent variable. Why bother with code? Just use the observed variable in a structural model if you don't think it has any measurement error.
No, but could you potentially, let's say, parsimony or preserving, you don't have enough degrees of freedom to have a full structural and measurement model in the same model. Would you, because you use too much power, could you set the value instead of 1 to, I think there's a formula
Yeah.
that 1 minus the
Absolutely.
Do you remember off the top of your head?
Oh, whether it's...
Yeah, you could incorporate the measurement error.
Yeah. Well, whatever the value is that you want to fix it to, you can just specify a to 1 by y1 at, instead of 1, like 0.8, 0.9, 0.7, whatever value you want to fix it to just extract the true part, whatever you think your estimate of the residual variance, the true score variance is going to be.
But isn't there a specific way that you can do the single indicator model in the structural?
Yeah, sure. I mean, whatever the formula is. If you only have 1 indicator in the data set, though, you have to estimate. You have to estimate. You don't even have enough information there to get a coefficient alpha or something, right? You have to go to the literature and say, oh, in the past, they've looked at the reliability. Like job satisfaction is the classic one. You know, all that research saying that it correlates with the larger scale at whatever value. And so you might use
Isn't
that.
that a shortcut where you can actually set a value equal to 1 minus lambda divided by standard deviation or something?
Yeah, for sure.
Is that
Yeah, well, whatever the formula is, and you just plug it in. The thing, though, is that in that case, the model is just identified. The model is just identified because you're imposing enough constraints in order to estimate it. How about this one? Same model as before, except instead of just one covariance, now we've got the slope and the covariance. No, because both of those reflect observed covariance among y1 and y2. Mplus, when it says, let me estimate the beta and the covariance term, where's it going to look? It's going to go to the sample, and it's going to look at the covariance there, the observed covariance. It's going to say, okay, well, how much of the observed covariance do I attribute to the beta, and how much of it do I attribute to this estimated covariance term? And as one goes up, the other can go down, and there's no best estimate. So this model is under-identified. It will not converge. So now that we know a little bit about how this works, identification, let's go to a more realistic case, and let's look at a CFA. 3 indicators, 3 residual variances. The first factor loading fixed to 1. This is what we were estimating before. The first factor loading fixed to 1. The other factor loadings estimated, and a latent variable variance also gets estimated. So let's start by looking at the implied covariance matrix. How many variances? 3. How many covariances? 3. 6 total pieces of information that the sample is going to give us. And how many parameters are we estimating here? 6. So it's just identified. But how is it identified? How do we know? How are we able to arrive at a best guess or maximum likelihood estimate for the 2 lambdas, the factor loadings, and the latent variables variance? The 3 observed covariances will help us estimate that. That's where we get the information to estimate those measurement parameters. And the residuals are really just the difference between the amount of variance that latent factor accounts for and the observed variances that we've got in our model. So it ends up being just identified. Does that make sense? At least in terms of the number of observed parameters implied by our data and the number of parameters we're estimating, you can see that they're the same. It's just identified. And specifically the measurement part of the model, which is going to rely on the observed covariances, because it's got to explain those observed covariances. We've got 3 observed covariances, and we really have kind of 3 measurement parameters here that will explain their observed covariance, and that's the 2 factor loadings and the latent variables variance. So, what about the next one? Turns out this is the same exact model as the CFA. In Amos, when you diagram it, how does it show residuals? Shows them as those tiny little, yeah, exactly. They're not big, important latent variables. They're tiny little, right? They're less relevant, but they're still latent variables. The residuals are not directly observed. They're not in the sample. They have to be estimated. And what is it really estimating? It's estimating a residual variance. Because whenever we talk about a variable, we're talking about a variance. So y1 eta 1 is defined by y1, y2, y3, semicolon. That's the top part of the model. At the bottom, do y1 and y2 and y3, do we have little double-headed arrows on those? No, we could say y1 at 0, y2 at 0, y3 at 0. No variance for those variables. And then we can just soak up whatever residual variance there should be with these other little latent variables that we put behind them. Eta 2 by y1, full stop. Factor loading of 1. And now, eta 2 is just the residual variance. It's just the error. It's just what's left over. It's still just identified, because you've taken the residuals from y1 and y2 and y3, and now you've just made them latent variables. Not that you would want to do that, but you can see how we're not actually asking Mplus to give us any more, right, any additional estimates compared to the regular CFA model. Okay, how about this one? Over, under, or just identified. Well, with 3 indicator variables, we've got in our CFA model 3 kind of measurement-related parameters, and those are the 2 factor loadings and the 1 latent variable variance. So it's 3 and 6 of those. How many observed covariances do we have? Well, it's 6 times 5 divided by 2. That's the number of unique elements in that lower diagonal matrix, right? So we have 15, because it's 5 plus 4 plus 3 plus 2 plus 1. So is it over, under, or just? Over, and it's way over. We've got 6 observed variances, 6 residuals, so that part of the model is just identified. And we've got 15 covariances, but only estimating 6 parameters that use those, that rely on those 15 covariances. Oh, sorry, duh. The bloody covariance, that's 7, sorry. 7. So, right? Take that away from 15 and you've got 8 left. Degrees of freedom are 8. The model is over-identified. No problem. Too easy. We can definitely estimate this. How about this? That's kind of a weird case. What do you think? According to our kind of, are there positive degrees of freedom? Is it over, under, or just identified? It's technically over-identified, because look, we're estimating 1, 2, 3 factor loadings for eta 2. Eta 2's variance, so that's 4. And then we've got 1 factor loading for eta 1, that's 5. And eta 1's variance, that's 6. So it looks like we've got positive degrees of freedom. We definitely do. But is the model identified? Can it arrive at a best guess for the measurement parameters associated with y1 and y2? No. Say it. Exactly. This part of the model is not identified. And the reason why is because in the observed data set, we only have 1 covariance, right, between y1 and y2. So when Mplus goes to estimate the latent variable variance and the factor loading, both of those have to rely on just the 1 observed covariance to arrive at a best guess. But just like with the paths going in opposite directions, if the latent variable's variance goes up, the factor loading could go down. The latent variable's variance could go down, and the factor loading could go up on y2. And both of those then would provide equally good explanations for 1 observed covariance. So this model, we would say it's globally over-identified because we've got positive degrees of freedom for the whole thing, but locally, and specifically in this part of the model, it's locally under-identified. This kind of under-identification can present problems because unless you know where to look and what to look for, you can estimate all kinds of stuff, and you'll scroll down an Mplus and it'll say, oh, model did not converge, there's a problem here, it won't give you estimates, there's some kind of issue, and you'll look at your degrees of freedom and you'll say, well, they're positive. So I know it's over-identified, but so what's the problem? The problem is you're asking for it to estimate 2 parameters based on only 1 observed piece of information. And that's the observed covariance.
What do you think that you put a with statement between eta 1
Right. So good question. What can we do to change the situation? Is there anything we can do to fix it? Well, let's check it out. For us, we can think about it as being like 2 models. because they're not connected at all.
You can add a covariance.
And this model is not identified, and that one is. So how can we create local identification? Well, we need to get more information from somewhere in the observed data set. We need to draw on additional covariances that we have so we can get our estimates, we can identify them and get best estimates. So one way to do it, right, that latent variable there has to look elsewhere for that information. And how is it going to do it? We can use additional observed variable indicators, or we can even do it like this. Whether you use an on statement or a by statement for that, it's all just regression, right? It's still just a slope, whether it's a beta or a lambda. So we can say eta 1 by y1, y2, and then you can say eta 2 on eta 1. And now, it's like that latent variable has 3 indicators. One of them is a latent variable. You might give that beta a substantive causal interpretation, but it doesn't matter in terms of estimation. Mplus doesn't care whether you say that's a measurement parameter or something else. The point is that now this model becomes identified, because you get to estimate those parameters, the lambda 2,1 and the psi 1,1, based on the observed covariance between y1 and y2 and all these other variables. Because check it out. Now, eta 1 is getting linked up to those other observed indicators, isn't it? It's not loading on them directly, or they don't load on eta 1 directly, but look, it's got like indirect effects down into those indicators, doesn't it? So we're still using those indicators as information to estimate these model parameters. So that's one way to identify a 2-indicator latent variable model. There might be some complaints from reviewers, because they'll say, no, that's not a real beta, that's like a lambda. You say, but it's just rise over run, right? It's just slope. Do you really care? And they'll say, well, they might have some substantive concerns about this kind of specification, but you can do it. You've got enough information to do it. Does this help us? It turns out it doesn't. We need regressions. We need to account for observed covariation in order to estimate these measurement parameters, right? This thing is supposed to be true score variance. True score variance is covariance among multiple observed indicators. This doesn't actually help us, because this doesn't help that eta 1 to explain anything. It's just a covariance there. It's not accounting for variation elsewhere in the model. Well, what if you don't want to do this just to identify it? What if you want to do something else? Well, we know now that the problem is that we're asking too much of our data in a model like this on the left. We're telling it to estimate 2 things, but it only has one piece of information to give us, to help us do that. So what can we do? Well, we need to institute parameter constraints. We just have to reduce the number of parameters that we're estimating, and then we can start identifying these models. What if on the left we had a model like this? We said eta 1 by, defined by, y1, that factor loading gets fixed to 1, doesn't it, by default? We can say y1 at 1, that would be superfluous, it's already constraining it to 1. And y2 at 1. Now how many factor loadings is it estimating if we fix those to 1? None. How many latent variances is it estimating? 1. And that latent variance estimate will be equivalent to the observed covariance, because that's the best guess. and we will get residuals. But really, it's just like, now the latent variable is basically just that observed correlation between the variables. That's kind of what it's representing. There's another way to do it. You can fix the first factor loading to 1 and eliminate the residual variance there. And then what have you got? What does y1 equal? y1 equals eta 1, doesn't it? Just like this. That's probably less useful, because why not just use y1 in the model for the latent variable? If you do this, a reviewer who kind of understands what's going on will say, yeah, but then eta 1 just equals y1. Why would you do that? The whole point is to correct for measurement error. You should have residual variance there in your observed indicators. There should be junk left over that doesn't get used in the structural part of the model. We're trying to correct for measurement error. This model, in theory, does that. Like, it doesn't do it very well. There are only 2 indicators, but you still have 2 residuals. What it's kind of like saying when you do this is it's like saying both of the observed variables are equally good indicators of the underlying latent variable. And the standardized factor loadings won't be 1, but they will be the same, arguably. Oh, close to the same. Point is you've just got one underlying. I mean, that would depend on whether or not the observed variance is the same. But the implication for measurement is pretty striking. They're both equally good or valid indicators of the underlying latent variable. And what that latent variable's variance picks up, or what it reflects, is the observed covariance. So you can do that if you want. What do you think? Maybe you don't want to fix those factor loadings to 1, because reviewers are going to look at that and say, hey, you're not estimating anything there in terms of, right, you're not actually correcting for measurement error in the way that I'm familiar with. I want to see factor loadings being estimated. Anyway, there are various ways. Let's not cover this. I think it'll just be a combination of annoyance and confusion probably at this point. But there are various ways to kind of make something like this look like it's a bit different, but actually you're still basically doing the same thing if you want to try and trick some people. And if, yeah, don't, forget it. Well, this is a big problem. The problem is that sometimes there are at least 2 problems. And one problem is we might not actually have enough information in the data set to get the estimates that we want. Our models might be underidentified. Right? Just globally. And another problem is that we might have what looks like enough information in the data set, but in one part of the model, it's actually locally underidentified. I mean, those are similar problems. So if you want to fix this problem, if you just have 2 indicators, for example, figure out what you're asking Mplus to estimate that your data might not be able to help you with. And then fix those parameters to some specific value, either 0 or 1, or do something, modify the model in a way that changes what you're asking it to do. Here's the thing, and this is kind of interesting. What if we have, let's go back to this. What if we have this model here, and this is locally underidentified, we cannot estimate it. Doesn't work. And then we say, oh, but we've actually got a different variable, y0, or whatever it is. And we didn't include it here. But let's include it as an indicator of eta 1, and now eta 1 has 3 indicators, and our model will be identified. And you include y0 in there. But y0 is actually perfectly correlated. It's correlated at 1 with y1. It doesn't actually add any unique information. It's totally redundant. You have actually not helped Mplus estimate that model at all, right? As correlations approach 1 among your observed variables, or -1, they're providing less and less unique information. So that can be a problem too. That can cause model underidentification. I mean, if a correlation is 1 or -1, just get rid of one of the variables anyway. You shouldn't be doing that. And actually, it'll cause problems with estimation for other reasons. So there are various, there used to be no singularly best way to figure out whether or not different parts of a model were identified. And then Judea Pearl, and I think probably one of his graduate students, released a paper I think it's in Psychometrica, and they talk about definitive rules for figuring out whether or not identification holds. But in most cases, you can just eyeball it. You can look and you can say, okay, we're estimating 2 factor loadings and a latent variable variance, and we got 3 variables, which means 3 observed covariances. We're good to go. So the rule of thumb is, for any latent variable, you need at least 3 indicators. They could all be latent, but you need 3. Non-convergence and matrix inversion problems, or singular matrices, which Mplus will tell you. Here's this problem. It'll give you when we scrolled down, we saw it was reporting errors to us. It was reporting issues with convergence. Can indicate local model underidentification. So particularly when we have theories that stipulate the bottom kind of relationship, we're going to run into issues, right? Job satisfaction and job performance. What are you going to do? Well, if they both influence each other, what's going to happen? If you have these these looping paths like this, you need additional information that you can bring into the model so you can identify those parameters. Formally, they would say the bottom one is non-recursive, which is weird because that's not the way you want to talk, but mathematically that's the language. So that model is not identified. Well, we had kind of a curious little case with instrumental variables, didn't we? We said, you can actually estimate those paths simultaneously. That's kind of simultaneity. As long as you have good instruments. Well, why does that work in terms of identification? It's an interesting question. How does it work? Well, if we bring in additional variables into the model like this, y1 predicts y2, but it does not predict y3. And y4 predicts y3, but it does not predict y2. This model is over-identified because we're estimating how many betas, 1, 2, 3, 4. And how many observed covariances do we have? We have 6. It's over-identified. And we can get unique estimates of beta 3 and beta 2 because we're not estimating effects of y1 on y3, and we're not estimating effects of y4 on y2. And the way Mplus gives us the unique estimate is it says, well, how do I explain the observed covariance between y4 and y2? How do I explain that? What information in the data set can I use to estimate beta 4 and beta 3? And it says, well, y4 and y2 have an observed covariance. So whatever beta 4 and beta 3 equal, they better equal something that explains that observed covariance. And now I can give you a best guess for those 2 beta weights. Because I can draw on the observed covariance between y4 and y2. And the same is true for beta 1, beta 2, right? Those estimates together, beta 2 in particular, right? Those estimates together should fit the observed covariance between y1 and y3. And now all of a sudden we can estimate those causal looping paths like that. And the power here, what allows us to get estimates of these two paths that normally we wouldn't be able to get is the fact that we're not asking Mplus to estimate a direct effect of y1 on y3. If we did that, there wouldn't be enough information in the data set. And the same is true y4 and y2. I think that's true. But anyway, certainly where the identification comes from is the observed covariance between y1 and y3 and y4 and y2.
Why did it become identified as a variable?
You mean if you don't have one?
You don't have one.
Yeah. Yeah, then you're sunk. If you want to estimate a model like this, you need additional information from somewhere. So to get those kind of looping causal paths, right, to reflect that kind of simultaneity in your model, you need additional variables there to act as predictors going into these two variables that are involved in that bidirectional causality. What's that?
Yeah. And they cancel each other out.
So that's important to know, right? You can, you know, y1 on y2, y2 on y1. You're not going to be able to estimate that. It's not identified unless you bring additional variables into the model. There's a lot of literature on models that look like this. And you can look it up under the topic of, or the heading or whatever, the name of non-recursive models or non-recursion in SEM. And it makes sense because a lot of people want to estimate models that look like this on the bottom. So how do you do that, right? To assume unidirectional causality in many cases is going to be a big assumption and one that a lot of people will question. So how do you get both of those paths in there? Anyway, if you want to read up on that topic, you totally can. Now, we haven't spoken much about the Bayes estimator, and I just want to maybe kind of whet your appetite here for this approach to model estimation, because there's a really cool feature of the prior probabilities when you use the Bayes estimator, and that is that estimation method treats the data as information to identify a model and its parameters. Right? It looks at the data to give you best estimates, but it also looks at the priors. So if the prior probabilities are giving you enough information to estimate a path that the data alone would not, then you can have identified models that with the maximum likelihood estimator would not be identified. And let me give you an example. Is this model identified? How many observed covariances would we have? 5 times 4 is 20, divided by 2 is 10. So we have 10 observed covariances. How many factor loadings? 1, 2, 3, 4. Plus the latent variables variance, that's 5. And now how many residual covariances do we have? 20, or 10. So that's 15, underidentified. We can't estimate all of those residual covariances. Those could go up, and the factor loadings could go down, and that would explain the observed covariances equally well. We can't get best estimates for a model like this. Unless we use a Bayes estimator, and we specify prior probabilities for those covariances. For example, we say they're probably 0. We think the scale is really good. We think we have residual covariances that are 0. So the mean, if we want to say they're normally distributed, we would say the mean of one of the residual covariances is 0, and we're pretty sure it's 0, so it's got a really small variance around 0. It's called a small variance prior. And the Mplus authors have written on this topic, and they've got examples of it for you in their papers. And then what Mplus is able to do using the Bayes estimator is use those priors, those small variance priors, as information to say, well, I'm not sure what the residual covariance is, but it's really close to 0. And if I try to go away from 0 too much, right? The likelihood of it being there, according to the prior, is not very high, and you will get convergence using that approach. So a model like this could be identified because the data and the priors both provide information for estimation. So there's some work on this if you're interested in it. You can check it out. But probably for the most part what you care about is under a maximum likelihood estimate, we're using a maximum likelihood estimator, right? Is your model and are your parameters identified? And that really has to do with whether or not you can get unique solutions to, right, to the question of what's the best estimate for some parameter. So if you run into problems, right, this might be why when you're estimating SEMs. And especially as your models get really complex, you might say, but I've got positive degrees of freedom. Why am I running into this estimation error? And it could be just because one little part of the model is, in fact, under-identified. And if even one parameter is under-identified, there is no best solution. There is no most likely estimate. And then you don't get convergence. And then if you're interested in the Bayes approach, you can look it up. So there's a lot of literature on model identification. This is just a very quick, rough intro to it. It would be irresponsible for you to know how to use on, by, and with statements and walk away and not know that this could be a colossal issue. Because all of a sudden you're trying to do stuff on, by, with, and it just doesn't work at all. You have to have at least a rudimentary understanding of what kinds of on, by, and with statements are going to lead to best guesses that Mplus is giving you, right? Maximum likelihood estimates. And so this is that. There are some nice little introductions to this topic. For example, in Klein's, I think he's got an updated book, Rex B. Klein. It's a great name, Rex. Rex B. Klein. Come here, Rex. Rex B. Klein. His book is actually really good. It's a wonderful introduction to structural equation modeling. And I think there's a new edition. It's like 2018 or 20, probably not 2011. But whatever it is, I think it's called Principles and Practices of Structural Equation Modeling. And he's got a chapter there where he talks about this. And he does so in such a nice introductory way. And then if you want something more technical, and you can look at Kenneth Boland's 1989 book, which is just kind of a Bible for structural equation modeling, but again, more technical. And that's it. So I would like to end on the high of SEM is easy, but it's important, I think, to to walk away saying, okay, I shouldn't just if I just jump into the deep end, I might sink. You gotta know why things don't work when they don't. So, okay, so thanks. I guess we're leaving a little bit early again today, and we'll come back. And tomorrow, we almost definitely will not be leaving early. So savor the flavor, because tomorrow's going to be different. Yeah, go ahead.